Hello students, welcome you to in this video lecture. In this lecture, we'll study how to trace a Cartesian curve. So basically Cartesian curve means a function which contains x and y variables. Okay, such curves we are going to trace. So here we'll require some basic definitions. So first is a double point. If two branches of a curve pass through a point, then this point is called as a double point. That means curve passes through this point two times, multiple points. If curve passes through a single point more than once, then such point is called as multiple point. So basically double point is also a multiple point. Node. Node is a double point such that tangents to two different branches of the curve are also distinct. That means two different branches and both are having distinct tangents. Then such point is called as node. Like in this diagram, this point P here is a node. We have two branches. For this branch, the vertical line this is a tangent, and for this branch this line is a tangent. So here we got two distinct tangents for two distinct branches. Therefore P is called as node. Next is a cusp. In previous case we had two distinct tangents. Now in this case, if for two distinct branches there exists a single tangent, that is the tangents are coincident, then it is known as cusp. Like in this diagram, here point O is a double point. See, this is one branch which passes through O, and this is a second branch which passes through O. So O is a double point, but for both the branches, this upper one and lower one, this horizontal line is a tangent. So we have single tangent for two distinct branches. Such point is called as cusp. Asymptote. Asymptote is a tangent to the curve at infinity. Like in this figure, this is graph of function tan x. This is a well-known graph. In this graph, this vertical line, the right side one, x is equal to pi by 2, is called as asymptote to this graph. Also, this line, the left one, this is also asymptote to this curve. Okay, so for this curve y is equal to tan x, there are two asymptotes. Basically this curve will not touch to this vertical line, the asymptote, but it will not cross to this line also. Such lines are called as asymptotes. Now there are some guidelines which we are going to follow to trace a curve. So for Cartesian curves, the equation of the curve may be in the form of y is equal to f of x, or x is equal to f of y, or we have implicit relation f of xy is equal to 0. So equation can be in any of these three forms. So first we are going to check symmetry. How to check symmetry about x-axis? So on changing y by minus y, if equation remains unchanged, then we have symmetry about x-axis. So when this will happen? When we have all the terms of y are in even degree. So when you change y by minus y, equation will remain same. Then we have symmetry about x-axis. Look at this example, y square is equal to 4ax. If you replace y by minus y, equation will not change, we'll get same equation. Therefore here we have symmetry about x-axis. See here, we have symmetry about x-axis. Or look at this example, y square is equal to x cube. Here also we are having symmetry about x-axis. In both the examples, look at the powers of y. All the powers of y are even here. Therefore we have symmetry about x-axis. Now next one is a symmetry about y-axis. So how will you check symmetry about y-axis now? So here we have to change x by minus x. And if the equation remains unchanged, then we get symmetry about y-axis. That means if all the terms of x are of even degree, then there is a symmetry about y-axis. Look at this example, x square is equal to 4ay. All the terms of x here are of even degree, 2. Okay. And this is a graph. This is a curve of x square is equal to 4ay. We have symmetry about y-axis. Now next is symmetry about both the axes, x as well as y. So when all the terms of x and y are even, then we have symmetry about both the axes, x and y. For example, this x square plus y square is equal to a square. This is a circle. We have symmetry about both y-axis as well as x-axis. Next is a symmetry about origin or symmetry in opposite quadrants. That means symmetry either, so graph will be same in first or third quadrant or second or in fourth quadrant, like this. So how to check symmetry in opposite quadrants? If the equation of the curves remains unchanged, if x and y are replaced by minus x and minus y, then we have symmetry about origin. Look at this example, x into y is equal to c. So here c is any constant. So let's take c is equal to 1. See, if you replace x by minus x and y by minus y, we'll get same equation. And this is a curve of this function, xy is equal to c. We have symmetry in opposite quadrant in first and third. Or look at this example, y is equal to x cube. If you replace y by minus y and x by minus x, we'll get same equation again. And this is a curve of this function, y is equal to x cube. We have symmetry in opposite quadrants. Now how to check symmetry about line x is equal to y? This is line passes through origin and passing through point 1, 1. So how to check symmetry about this line? So to check symmetry about line x is equal to y, we have to simply interchange x and y and check if equation remains same or not. If equation remains same, then we have symmetry about line x is equal to y. Look at this example, x into y is equal to c. So in this example, if you replace x by y and y by x, you'll get same equation. This is a curve of this function, xy is equal to c. So here we have symmetry about line x is equal to y. Now how to check symmetry about line x is equal to minus y? So replace x by minus y and y by minus x simultaneously. If equation remains same, then there is a symmetry about line x is equal to minus y. Look at this example, xy is equal to minus c. So again here, if you replace x by minus x, x by minus y and y by minus x, there is no change in LHS. So equation remains same and we get this curve. So here we have symmetry about this line x is equal to minus y. So this is how you can check symmetry about line x is equal to minus y. In this part, we'll see how to check whether curve passes through the origin or not. We get lot of information when curve passes through some points. Like, imagine the graphs of sin x and cos x. The graphs are almost identical. The only difference is graph of sin x passes through origin and the graph of cos x does not passes through the origin. So that is the only difference. So checking whether the curve passes through the origin or not gives us very much information. So how to check that? So if the independent constant term is absent in the equation of the curve, then it passes through the origin. That is, if we replace x by 0 and y by 0 and equation satisfies, that means the curve passes through the origin. So basically, when 0, 0 satisfies the equation of the curve, then that curve passes through origin. And this will happen only if there is no independent constant term in the equation. Look at these examples. X cube plus y cube is equal to 3axy. In this example, there is no independent constant term. So when you put x is equal to 0 and y is equal to 0 in this, so LHS will be equal to RHS. Therefore, curve will pass through the origin. Or in this also, look at the second example. Here also there is no independent constant term. So when you put x is equal to 0 and y is equal to 0, we'll get LHS is equal to RHS. This is a graph of x cube plus y cube is equal to 3xy. So it passes through origin. And this is curve of the second equation. This also passes through origin. Now next important thing is tangents to the curve at origin. Tangents are the most important things when you trace a curve. Tangents decides the shape of the curve at that point. So how to find tangents to the curve at origin? If the curve passes through the origin, then the tangents to the curve at origin can be obtained by equating to 0 the lowest degree term of the equation. So we have to equate to 0 the lowest degree term in the equation. Look at this example. X cube plus y cube is equal to 3axy. So here lowest degree term is 3xy. You equate with that 0. So we get x into y is equal to 0. That means either x is equal to 0 or y is equal to 0. Which are basically lines passing through origin. X is 0 is what? It is a y-axis, and y is 0 is x-axis. Both are the lines passing through origin. Hence the tangents at origin are x is 0 and y is equal to 0. So this is that curve which passes through origin twice. So here origin is a double point, and for this portion, the upper one, x-axis is a tangent, and for this portion y-axis is a tangent. So this point here is a node. Look at this equation. So lowest degree term here is a square into bracket y square minus x square. If you equate that term with 0, we'll get y square is equal to x square. That means y is equal to plus or minus x. So here also we got two lines, y is equal to x and x is equal to y is equal to minus x. So these are the two lines, y is equal to minus x and this is y is equal to x. So both are the tangents to the curve at origin. Now points of intersection. So points of intersection with y-axis. So we'll see how to find points of intersection with y-axis. Put x is equal to 0 in the equation and find values of y. Points of intersection with x-axis, you have to put y is equal to 0 in the equation and find values of x. Now nature of a tangent. So here we'll see how to find tangents at other points other than origin. So to find the nature of the tangent at any point AB, the first thing we find dy by dx at that point. So this gives us a slope of a tangent at point AB. Now for the curve of the form f of xy equals to 0, dy by dx is minus fx upon fy. If dy by dx is equal to 0, then tangent will be parallel to x-axis because slope is 0 and for horizontal line slope is 0. So tangent will be parallel to x-axis. If dy by dx is infinity, then tangent will be parallel to y-axis. If dy by dx is greater than 0 in the interval a to b, then y is an increasing function in that interval a to b. If dy by dx is less than 0 in the interval a to b, then y will be decreasing function in the interval a to b. Now next is asymptote. So asymptotes are also tangents, but these are tangents at infinity. So how to find asymptotes parallel to x-axis? So these are obtained by equating to 0 the coefficient of highest degree term in x. So look at this example, xy is equal to 1. Highest degree term in x is x only and its coefficient is y. So equate y is equal y with 0. So we get line y is equal to 0 is x-axis, which is asymptote parallel to x-axis. This is a curve of this function xy is equal to 1. These two branches, the green color branches, and for these branches x-axis is asymptote. It is a tangent at infinity. Now next is asymptote parallel to y-axis. These are obtained by equating to 0 the coefficient of highest degree term in y. So in this equation xy is equal to 1, highest degree term in y is y with and its coefficient is x. So we have to equate x with 0. This is a line y-axis. So this is asymptote parallel to y-axis. This is a curve of this equation xy is equal to 1 and y-axis is asymptote parallel to y-axis. So this is how we are going to find asymptotes parallel to x-axis and parallel to y-axis. In this video, we'll see how to find asymptotes which are not parallel to coordinate axis. Such asymptotes are called as oblique asymptotes. Such asymptotes may exist when we have equation of the curve in this form, f of xy is equal to 0. The procedure is, we'll assume that y is equal to mx plus c be the asymptote. See, asymptote is a tangent to the curve at infinity, and tangent is nothing but a straight line. So we'll assume that straight line is y is equal to mx plus c, and we'll try to find values of m and c. Now this straight line will touch the curve for some values of m and c. Therefore solving f of xy is equal to 0 and y is equal to mx plus c simultaneously, we get required values of m and c. For example, we'll try to find asymptotes for this curve. X cube plus y cube is equal to 3axy. This equation can be written in this form, f of xy is equal to 0 by taking this 3xy in LHS. So let y is equal to mx plus c be the oblique asymptote to this curve. So replace y is equal to mx plus c in this equation. We get this equation. When we open this bracket mx plus c cube, we get this equation, 1 plus m cube x cube plus 3m square c minus 3m into x square plus 3mc square minus 3c into x plus c square is equal to 0. So in this equation, we will equate coefficients of two consecutive higher powers of x. So we'll equate 1 plus m cube, which is coefficient of x cube, with 0, and coefficient of x square, which is 3m square c minus 3m with 0. Solving these two, equations, we get m is equal to -1 and c is equal to -1. Now put these values of m and c in the first equation, y is equal to mx plus c. We get required asymptote, y is equal to -x minus 1. So this is that line, y is equal to -x minus 1, which is asymptote for this given curve. So this is how we will find asymptotes which are not parallel to coordinate axis. Region of offsets. Now next important point is we have to check in which region curve is not present. So the procedure is, we'll mark x-intercept or y-intercept and asymptotes if any, because generally curve does not exist beyond the asymptote. So try to write equation in this form, y square is equal to f of x. If it is possible, then try to write equation of the curve in this form, y square is equal to f of x. And if for any value of x, y square is negative, so when y square is negative, y is imaginary. For such values of x, curve does not exist, because we are going to plot only real portion of the curve. So here we will first try to write equation of the curve in this form, y square is equal to f of x. If y square is negative for x is less than a, so when x is less than a, if y square is negative, then there is no curve to the left of the line x is equal to a, because whenever x is less than a, that means whenever x lies to the left side of a, y square is negative and therefore y is imaginary. Or if y square is negative for x lies between a and b, when x is between a and b, if y square is negative, that means curve does not lies between the lines x is equal to a and x is equal to b. Third, if y square is negative for x is greater than a, that means when x lies to the right side of b, y square is negative, then there is no curve to the right of the line x is equal to b. Similarly, we can find region of offsets for x square is equal to f of y. Same procedure we have to repeat for second part. Note, sometimes we may confirm the region of offsets by simple observation. For example, equation of a circle, x square plus y square is equal to 1. So in this case, whole curve will lie inside the region x where x minus 1 to plus 1 and y minus 1 to plus 1. So in that square only the whole curve will lie. So this is how we can find region of offsets. Or for example, y is equal to sin x. The whole curve will lie between two horizontal lines, x is equal to -1 to x is equal to +1. Or look at this, x into y is equal to c. So here curve will not present in second and fourth quadrant. It will present in only first and third quadrant. Second point, if there are 2 points on the line of symmetry, then curve exists in between, then there is a loop. So when we have symmetry about any line and our curve intersect that line at 2 points, then there exists a loop between those 2 points.